Hello, and in this video we're going to have a quick overview of templates. Again, this is an advanced subject where I'm just going to give you a quick feel for what's involved, so you'll be able to understand what's happening when you see it in other people's code. Okay, so let's get started. I've written a function here called max, which compares two numbers. If the first number is bigger than the second, we return the first one. Otherwise, we return the second one. So that's pretty straightforward. I've called it max with a capital M because there's already a function max with a lowercase m in the standard library, and I don't want to get any conflicts when I compile this. Okay, so that's fine. Then I discover that you can actually compare strings by calling the greater than operator, which will go through and compare each character. So for example, if we have strings ABC and ABD, it'll see that A is the same in both strings, B is the same in both strings. Then it'll see that one string has C and the other has D. D is regarded as greater than C, so it's going to regard ABD as greater than ABC. So I'm going to write a function here called max as well, overloading the max function to take strings and doing exactly the same comparison. Now if you look closely at these functions, you'll observe that everything about them is the same. The only difference is the type of the variables and the names of the variables, which doesn't really matter. I could have equally well called these D1 just to make it the same. So if I replaced string by double in this function, it would all work exactly the same as this function. So basically I've written the same function twice, but for different types. And then maybe I might go on and there's some other classes from the standard library or classes I've written myself that I wanted to compare. Every time I want to compare them, I'm going to write a new function which is exactly the same as the existing ones but for a different type, which is all rather repetitive. Generally, when you find that you're repeating yourself when you're writing a program, that's usually a sign that you should stop and have a think about whether there's a better way to do that. And in C++ there is a better way to do that, called templates. So in C++ we can write a function template. We give the compiler a template to show it what the code looks like, and we use a dummy type T, so instead of putting a double or string I put capital T here. It's just a convention that it has to be capital T. It could be anything really, but people always use T. This mysterious bit of code here tells the compiler that it's going to be a template function because of the keyword template. Then the angle brackets tell it what the template type or types are, because you can actually have more than one type. In this case I've just got one type, capital T. Then we put the type name keyword before that. So template angle bracket type name and then the name of the dummy type. Then I write the function exactly the same as before, but with double or string replaced by T. And then what will happen when we try to use this function, the compiler will go in and replace T with the appropriate variable. So for example, if I want to use this with doubles, it'll go in, it'll replace T with double, and then it'll actually generate a new function which has that code. So this is really an extra level of programming. We're telling the compiler how to generate code. Okay, so let's see how this actually works when we use it. So all we have to do is just call the function with some arguments. Obviously the arguments have to be the same type or something that can be converted to the same type. So in this case I'm using 7.0 and 2.6, which are both doubles. The compiler will look at these, it'll realise that max is a template function and we're calling it with doubles, so it'll go away and generate a version of max which uses doubles. And in fact it'll generate exactly the first function that we had before, with max taking doubles and returning a double. So this is known as instantiating the template or template instantiation. So in effect the compiler creates a version of this function in which T is replaced by double. This process of working out which type to use is called deduction, so the compiler here is deducing that the arguments are doubles. Because we're operating on an extra level of abstraction, if you like, we're having the compiler writing code for us. This means that template functions require us to organise our code slightly differently from regular functions. So if we remind ourselves of what happens when we call a regular function, the compiler will check this function call against the prototype for the function. It'll make sure that we're using the right types. So the compiler only needs to be able to see the declaration of the function, which will give it the function signature. So that'll give it the number of arguments, the types of the argument, whether the function is const or non-const, and so on. For a template function, it needs to be able to do a lot more. When the compiler sees a call to a template function, it has to be able to get the template definition and replace the type t by the actual type. So that means the compiler has to be able to see the full definition of the template function. And if it can't see the full definition, then it can't instantiate the template and generate the necessary code. So that means we need to have some way of letting the compiler know what the definition of the template function is. The obvious way to do that is just to write out the full template definition in the header file, and then it gets automatically included along with the function prototypes for normal functions. And that's actually what most programmers do. However, some programmers prefer to put all the template codes in a separate file and then include that file as well. So you may have a file called .inc, which has all the template definitions, and then they just put the prototype for the template function in their header file. It's a matter of taste really. Personally, I prefer to do it this way. I suppose there is the argument that if you put the template definition separately, then whoever's using the header file can't look at the definition of the template function. So maybe that's an advantage. Okay, so that's function templates. There are also class templates. So we can write classes that can work with any type of data. So here's an example of how we do it. Again, we put template angle bracket type name t to let the compiler know that this is going to be a template class and that the dummy type is going to be called capital T. Then we have the normal class definition, so the class and the members and the member functions. The difference is with a template class we can use data which is of the dummy type, so we could have member variable here called data, which is of type T. So when this gets instantiated, this is going to be replaced with an int or a string or a vector or whatever it needs to be. And we can also have member functions which are very similar to template functions, except that the compiler already knows it's a template, so we don't need to put template type name t in front of it. So here we have a constructor which has the same name as the class. That's how we know it's a constructor. The constructor will take an argument of type t, and then it'll initialize our data member using the argument to this function. Obviously, in a real class you'd make the constructor public, otherwise you wouldn't be able to create any instances, but this is just an example. And then when we instantiate this class, so we want to create an instance of the my class. So we put my class, then the variable name and the constructor arguments, but we have to put the type that we want to instantiate with in angle brackets. So it's my class, angle brackets, string. That'll generate a version of my class with string as the type here. So my class with string is actually a class which has string here. So I'll briefly talk about the concept of generic code. Generic code means you write your code in such a way that you can use it with any type of data. And we've seen an example of this, which I've probably mentioned quite a few times. The standard vector can store elements of any given type, including built-in types and types that you've written yourself. This is also known as parameterized code. So the type is a parameter that determines which version of the code gets used. In vector, angle brackets int, the parameter is int. So this means we use a version of vector which can work with int. But the actual vector part of the code is all the same. It's just the part that deals with the elements that's different. So the advantage of this is that we can concentrate on the algorithms the program is using for processing data, rather than being focused on what type of data we're working with. And as you've probably guessed, in C++ we use templates for doing generic programming. Here's an example, very simplified example of how the vector class is implemented. If you look at the vector header file in your compiler implementation, you'll see it's very complicated. There's lots of strange things in there which you aren't really meant to understand. So don't worry if it doesn't make any sense, because it doesn't for most programmers. So here again we have class vector. It's a template class, so we have the template type name t, and then there's some code in here which will manage a vector of elements of type t. So when we have a vector of int, this will instantiate it with t replaced by int. When we have a vector of string, this will be instantiated with t replaced by string, and so on. And all these versions of vector will function the same way regardless of what type of element we use. So that's how to implement generic programming in C++. Okay, and finally, one last note before I finish off this video. I've used the type name keyword in these template examples. If you're looking at older code or code written by older programmers, you'll see use the class keyword instead. You can actually use both. The type name keyword was added in C++ 98. The reason for adding it is that if you have class t in the template declaration, people sometimes thought you could only use it if t is a class, or if the template is a class template. I'm not sure if that was really true, but anyway, they thought it would be useful, so there you are. You have two different ways of doing it. Type name is probably the best way to do it, but you can still use class if you want to, and many programmers still do. Okay then, so let's sum up this video. So templates allow us to write the same code for different types without having to write the same code over and over again. When we write the template function or the class template, we use a dummy type. When the compiler instantiates this template code, it will generate a version of the code in which the dummy type has been replaced by the type that we need. We can use templates with both functions and classes. And finally, templates are used for generic programming in C++. Templates are quite an advanced topic. They can get very complicated. In fact, someone discovered that templates are a complete programming language in themselves. So you can actually write a program that runs inside the compiler, which is very powerful but very difficult. That's probably going to be in the advanced course. But anyway, until then, until the next time, keep coding.